Hey guys, what's up? As you see here on the screen, not sure if you recognize it or not, but this is actually in Las Vegas at a very famous hotel called the Bellagio. And this Bellagio has been in many different movies. And what you see dancing there on the screen is fountains. Oh, look at those pretty parabolic shapes. Oh, yep, that's why they're on there. But I don't know if you know this or not. You can go type into YouTube the Bellagio. It's spelled Bellagio. But there's all kinds of different videos that's on there. The one that you see on the screen is actually set to the Titanic theme music. It's really beautiful. But you see these things here throwing the water up in the air in all kinds of parabolic shapes. And what I'm going to show you in this video is how you actually do things called projectile motion questions. And the bottom line is, as the water here is shooting out of the actual surface of the water, it's flying up in the air and gravity's taking a hold of it and it's pulling it back down to the pool. Huh, pulling it back down to the pool. That's funny. But you can see sometimes it shoots up in the air, sometimes it goes to the right, the left. The point is, if it's shooting to the right or to the left, the shape that the water droplet is going is in a parabolic shape. It's going up and then coming back down. So what we're going to do is actually come up with a question that is from this Bellagio, from this fountain, and we're going to find out how far a water droplet would actually go. And the question would be, if I shot a water droplet up in the air, how far would it actually go if it was going at a certain, distance or speed? And all those things, if you're sitting there wondering, like, well, yeah, it all matters. How hard is the actual? What's the velocity of the water droplet coming out of it? What angle is it going? Is there any wind speed? Is there anything else? All that is very important, no doubt, in determining the answer. And yes, believe it or not, the famous and wonderful smart people out there came up with what they call a vertical motion equation, and we're going to talk about that. So what you need to do, let me stop this thing here, woo, is get out the graphic. Well, it's not the graphic organizer. It's the example I gave you in class. That it has this example written on it. It says, the water at the fountain at the Bellagio in Las Vegas leaves the spout with a vertical velocity of 80 feet per second. If the spout is 224 feet above the level of the pool, so this is a little bit different in the example of Bellagio, how long will it actually take for a single drop of water to travel from the spout to the pool? And as I told you, the vertical motion equation, which is on your sheet of paper, is this right here. Now, I'm going to have you, on your sheet of paper, take some very important notes of what the H stands for, of what T stands for, of what this V sub 0, or some people call it V naught, stands for, and what the H naught or H sub 0 stands for. So make sure you got that out and get your pencil or pen ready. Here we go. So here is your equation, and what the H stands for, and you need to put this on your sheet of paper. The H actually stands for the height, the height of whatever object it is. Now in this example, we're talking about shooting a water droplet up in the air, and you could be throwing a ball, you could be kicking a ball, you could be throwing something off a cliff, it could be a penny, it could be a cannonball, whatever. It's the actual height of the object, wherever it is. So that H at any time, whoops, there we go, the T, here we go, the T, they stand for the time, so how many seconds that the object is in the air. So at a certain time, you can say, okay, so if I say, for example, at time, 3, you can plug 3 in here for T, if you got some other numbers, and you can figure out the height of the object, wherever it happens to be. So that's what that stands for. Now, we also have in this example with the water droplet, it says initial velocity. That is, let me change colors, that is this right here. The initial velocity always is the V naught. So this, you can write in your notes, is the initial velocity. And over here, the H sub 0, change colors again, this actually stands for the initial height. So whenever we actually launch this object, whether it be again the a ball or a cannonball or a penny or the water droplet, the initial height is what you'd substitute in here to this vertical motion equation. The initial velocity you'd substitute in there. If you knew the time, you'd substitute it in there. If you knew the actual height of the object at a certain time, you'd substitute that in there. So all of those things are very important to know in doing this question. Now, back to the actual question itself underneath the vertical motion equation on your paper. So what we're going to do with this example is a bunch of different things. First of all, we're going to write the equation. that represents this vertical motion question. We're going to B, find the t-intercepts. We're going to C, find the h-intercepts, what they actually are. Woo. We're going to then find the vertex, and then overall we're going to actually take this thing and graph it. The height equation, it's going to be a rough sketch, there's no doubt, because the numbers get pretty big when you do these things. But that is exactly what we're going to do. But ultimately the question is this. We're finding how long it actually took for the water droplet to hit the pool level. That is the deal. So I'm going to fire some things at you here very quickly. You can pause the video, but make sure you take notes on this, because the notes here will be applied for what we're going to talk about in class and be used. So make sure you pause it, study this, and here we go. To find the answer to the first one, write the quadratic equation that represents this vertical motion. It's this simple. You simply plug in the given values into the vertical motion equation. You're given the vertical velocity, the initial velocity, the vertical velocity, right there. And you're given the actual spout is 224 feet above the actual level of the pool. There it is. So all you have to do is plug that in. So let's go do it. So let me pull this down here a second so we can do it. Okay. So I'm going to put my numbers in there. Again, the initial velocity, here would be my equation. This is A. Let me get this over here. So A, letter A. The height is negative 16 t squared. My initial velocity, it told me, was 80, so it's positive 80. It doesn't say negative 80, it says positive 80. I'm throwing the actual, back up. The initial velocity right there is positive 80, so bing, it's flying up in the air. And I don't know t, we don't know that. But I do know the initial height, because it told me that the spout itself was 224 feet above the surface of the pool. Now, if it was right at the pool, then the initial height would be 0. If it was below the pool surface somehow, then it would be negative. But that particular thing right there, the initial height, is just positive. Now, here's an important thing to tell you about initial velocity. If you're throwing an object up in the air, the initial velocity then is positive. If you're throwing the object down, then the initial velocity is negative. So that has something to do with this right here. So again, re-listen to that so you got that idea. Initial velocity is positive because I'm throwing the actual water droplet up in the air like this. That's why I put positive 80. Okay? So there's letter A. So how do I find letter B? How do I find the t-intercepts? And the t-intercepts is nothing more, guys, than really just the x-axis. The t-axis is the same thing. So I'm looking for where that parabola is going to cross the t-axis. Oh, that sounds familiar. Where the parabola crosses the x-axis, aka the solutions. And yes, this is how we do it. You plug in 0 for h, and then you solve it. That is exactly how you do it. So you plug in 0 for h, and then solve. How do you solve it? Whether you want to use the quadratic formula, or the square root method, or factor in ZPP, 100% up to you. But that is how you find the t-intercepts. Now, how do we do letter C? Letter C is this, the h-intercept. The h-intercept is nothing more than where the parabola crosses the y-axis. There's missing an s there, sorry. I should say axis. So the h-intercept is where the parabola crosses the y-axis. How do you find that? You plug in 0 for t, and then simply solve it for h. Because as soon as you plug in 0 for t into the vertical motion equation, which, by the way, if you're wondering what that is, here, it's this guy right here. It's negative 16. That's what we did in letter A. I'm not showing you other work because you can do it yourself. That's the actual equation. So I'm going to plug in 0 for t, and as soon as I plug in 0 for t, those guys really just wipe out, and I'm just left with whatever h is. That is exactly what this is telling you. That finds the h-intercept for the parabola. Great. How do I find letter D, the vertex? Oh, yeah, we've done this before, the vertex. I have to use this equation and my negative b over 2a, that negative b over 2a, back here in this thing, right here, negative b, there's the b, there's the a, so negative b over 2a will give me my exact t-intercept right here. So that's my t value, the x-coordinate, the t-x-coordinate, whatever, same thing, for my vertex. And yep, then I got to plug that back into the equation, the overall equation, and that'll give me my y, aka the h, this guy right here, the h, that guy. It'll give me my h value. So that's how you find the vertex of this parabola. And then letter E is just graphing the height equation using your work from B and D. So you plot all the 4 points. So the two t-intercepts where it crosses the t-axis, the horizontal axis. You find the h-intercept where it crosses the actual y-axis. Oh yeah. And then you find the vertex, which you already got, and you put that dot on there, and that tells you really exactly how the parabola is going to look. Exactly like that. So those 4 points right there will help you graph the parabola. Boom. But here comes the question. How long did it take for the water drop to hit the pool level? So what I've done for you, notice this. Here it is. This is the graph. This is maybe what yours looks like. I have no idea. You got to pick the scale for the y, or well, not the y-axis. It's now the h-axis. It's the h-axis. H-axis. This one here is the t-axis. You got to pick your scale for this. I'm just showing you very bare bones minimum what this thing is looking like. You're going to have numbers on this. So if you're like, why isn't Mater doing it? Because you can calculate it yourself. I want you to find this point. I want you to find this point. And by the way, this right here is where the actual spout is. Woo, that's actually shooting the water droplet out of. So it's coming out of here. Remember, it said at a certain height. So this, well, I'll give this away. This right here should be 224 because over on the question, I believe, let me look. Yep, it said 224 feet. So at 224 feet, that's where the initial velocity starts. Boo! It comes up here at the vertex, which you should have found. And then it comes down here. And oh, by the way, yes, bam, 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 bam. That spot right there is where the water, it's where the water drop hits the actual pool. So the question was, how long will it take for a water drop of water to hit the pool? Remember the t here, the t-axis represents the seconds. Oh, look at me. So the t here at 0, tick, 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 tick. As soon as this baby goes boom and shoots it out of here and kicks it up in the air, the time starts ticking. Tick, 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 tick. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, however many it is, until it hits the ground. So you are looking, yes, for that spot right there. So, yeah, come to class with answers to all of these. The vertex, the h-intercept, the two t-intercepts, and that thing right there is going to be your answer, the solution to how long it took for, boom, this water drop to go up, start coming back down, and bloop, splash and hit the water level. So there you go, guys. That is an example. Go back and study it because we're going to use it a lot. See you in class. Later.